Good day everyone. Today we are going to discuss the group project for TAO 6123 Computer Architecture and Organization. Our lecture session is A01 and our tutorial session is 1A. We are from group 3. Our group members include Lim Jiaqi, Lim Jiashen, Ko Shanxi and Ko Kaixin. Here is our table of content. Now I will pass the presentation to Jiashen.
Thank you, Jiaqi. Hi everyone, my name is Lim Jiashen. So now I'll be presenting an overview of 4 research papers related to computer architecture. First, the first research paper proposes a new RISC vCPU design with an extended pipelines that reduce wiring complexity while maintaining high performance. It replaces the parallel functionals unit with sequentials 1 in different pipeline stages. FGPA implementations also show 2.64 times better power efficiency and 1.42 times fewer multiplexer compared to traditional designs. Next, this paper authored by Muthu Kamaran in 2025 focuses on improving memory performance in high-performance computing. It introduced techniques like loop dialing, NUMA, awareness, and 3D stack memory to reduce latency and improve bandwidth. These strategies help address bottlenecks in memory access and enhance overall system efficiency. Then, the third paper titled Complete Analysis of the Cache Architectures for Better Performance focuses on the role of cache in enhancing system performance. It provides a detailed explanation of the 3-level cache hierarchy, L1, L2, and L3 and examines how these layers contribute to the speeds and efficiency. It also explains how improving cache structures helps reduce miss rate, lower latencies while managing data consistency and coherence effectively. Lastly, the final research paper, which in 2024 by Li-Fu Deng, presents a 5-stage pipeline RISC vCPU built-in Verilog and Vivado. The design supports the RV321's instruction set with multiplications functionality and follows a 5 classic 5-stage pipeline: fetch, decode, execute, memory, and write backs. It emphasizes improvements in the ALU, decoder, register files, and branch unit, demonstrate a practical and optimized processor implementations.
Thank you, Jiashen. So now I will talk about the difficulty faced in part A. In the first part, we had to find a research paper related to computer architecture published in the last 5 years. This was harder than we expected because many papers didn't match our topic or were too old. Then the paper were also full of difficult technical terms which made us hard to understand. Besides, we spent a lot of time rewriting the content in our own words, and some of us found it extra challenging due to have less experience with academic reading. Last, it also took effort to figure out and explain what parts of the paper were strong or weak. Next, I will talk about the benefits in part A. Through all the difficulties, we improved our academic reading and writing skill. We learned more about topics like processors, memory, and system performance. Besides that, it helped us practice explaining complex ideas in simpler ways, and we got better at thinking critically about research.
Thank you, Shanxi. Hi, my name is Kaixin. I'm going to explain the overview of SMP Cache Simulator. For part B of our project, we explore a simulation using SMP Cache Simulator, which is a tool designed to model cache memory performance in uniprocessor systems. This simulator is particularly useful for studying how different cache size impact miss rate when running various types of programs. The system was configured with consistent architecture, which is one processor, messy protocol, fully associative mapping, and an RRU replacement policy. We ran simulation on 9 real-world memory trace files, adjusting the cache size from 1 blocks to 512 blocks, which is equal to 0.03 kilobyte to 16 kilobyte. The simulation workflow included setting the cache size, loading a trace file, selecting how to view output, and executing the full simulation. The following figure shows the cache evolution in different formats, which is text format and graphic format. In our discussion, we found several key patterns. First, miss rate consistently decreased as the cache size increased. For instance, Hydro dropped from 66% to around 14% as cache blocks increased. However, a larger cache can also result in a longer access times and higher power usage, so it is important to find the right balance between size and efficiency. Second, different trace files show different behaviors. While all reduced their miss rate with more cache, the rate of change varied. A standout case was the CXP trace, which dropped sharply from 14% to just 1.5% between 8 and 60 blocks. This shows that some programs require less cache to perform efficiently, and others need more. Some traces even plateau earlier, revealing difference in access patterns. Next, because we use a fully associative cache, conflict misses were eliminated, so all misses were due to limited capacity. Traces with more predictable access patterns saw faster reduction in capacity misses as cache increased. We also observed that miss rate eventually stabilized. After a certain point, increasing the cache size has little to no improvement. This saturation point occurs when the cache can store the entire working set, minimizing data replacement. Identifying this point is helpful for optimizing performance and cost. Lastly, we found that program behavior plays a huge role in cache performance. CXP performed well with a small cache, while Hydro and NASA 7 needed much larger one. Programs with tight loops or frequent data reuse benefit more from even smaller and well-configured cache. That's all from me. Now I'll pass the presentation to Shanxi.
Thank you, Kaixin. So now I'll talk about the difficulty faced in Part B. This tool was quite old and had very limited instructions, so the setup was difficult. Then we had to try many times to get it running properly. Also, some of us were not familiar with low-level hardware concept like cache mapping or block size, so interpreting the result was a challenge. The benefits in Part B, including we gained a real hands-on experience with simulation tools, like we saw how cache size can affect miss rate and performance. It helped us connect what we learned in lectures to practical outputs, and we worked closely as a team to understand and discuss the data together.
Thank you, Shanxi. Now I will present Part C, GitHub overview. Git is a free and open source tool created by Linus Torvalds in 2005 to track code changes. It was designed to be fast, secure, and to replace older tools like BitKeeper, which were not free and harder to use. Git is useful because it tracks every change in the code, supports teamwork, and stores code online for easy access and sharing. For our project, I, as the group leader, created the GitHub repository TLO/123_1A_group3. I initialized it with a README file that includes our project description and admit license to allow the open source permission. I also added my group members as collaborators and committed a file called members.txt. After that, each group member added their name to members.txt using GitHub Desktop. The workflow we followed was clone, edit, commit, and lastly, push. Our commit message were clear and descriptive, such as add the Kaixin to members.txt. All changes were traced successfully with no conflict, and the history tab on GitHub shows every commitment. We also can view the updated members.txt file, which includes the full names of all group members. Now, let us look at the Git version control system. Git was created by Linus Torvalds in 2005 for Linux development. It is a distributed version control system, meaning each developer has a complete copy of the project. Git allows us to track changes, manage code history, and work offline. As for the difference, Git runs locally on our machine and works even without internet, where GitHub is an online cloud platform that hosts Git repositories and provides a web-based interface for collaboration. Key features of Git include full project history available offline, easy branching and merging, as well as secure tracking using cryptography hashing like SHA-1. For team projects, Git helps to detect and resolve conflicts, enable code review through pull requests, as well as allow bug fixing by reverting to earlier commits. For mixed language project, Git supports tracking for all file types like assembly, Python, and Java, as well as enables modular and cross-platform development. GitHub provides reliable backup and remote access for the entire team.
Thank you, Jachi. So now I will talk about the difficulty faced in Part C. We learned how to create a repository and use GitHub to collaborate as a team. It was tough at first, especially resolving conflicts when we edit the same file. Other than that, writing clear commit message and organizing commit took some practice. Managing changes from multiple members showed us how important good teamwork really is. Though this path is challenging, but also gave us valuable skills, like we learned how to use Git and GitHub in real projects. We understood how team works together in coding, how to manage and track our progress, and how to keep code clean and organized. Besides, it really improved our teamwork and gave us a good foundation for future software development projects.
That's all for our presentation. Thank you.